Okay, now what I'd like to talk about is the solution. What is it I have to do to solve the equation? So to solve that equation that I outlined in orange on the board, the ODE, our task is to find two solutions. Now, don't make it too trivial. There's a condition that solution should be independent. All that means is that y2 should not be a constant multiple of y1. I mean, if you got y1, then 2 times y1 is not an acceptable value for this, because as you can see, you really only got 1 there. You're not going to be able to make up a 2-parameter family. So the solutions have to be independent, which means, to repeat, that neither should be a constant multiple of the other. They should look different. That's an adequate explanation. Okay. Now, what's the basic method for finding those solutions? Well, it's what we're going to use all term long, essentially, studying equations of this type, even systems of this type with constant coefficients. The basic method is to try y equals an exponential. Now, the only way you can fiddle with an exponential is in the constant that you put up on top. So we're going to try y equals e to the r t. So I'll use t as the deep. Notice you can't tell from that what I'm using is the deep independent variable, but this tells you I'm using t, and I'm switching back to using y as the dependent variable. So t is the independent variable. Why do I do that? The answer is because somebody thought of doing it, probably Euler, and it's been a tradition that's handed down for the last 300 or 400 years. Some things we just know. All right, so now if I do that, as you learned from the exam, it's very easy to differentiate exponentials. That's why people love them. It's also very easy to integrate exponentials, and half of you integrated instead of differentiating. But so we'll try this and see if we can pick r so that it's a solution. Okay, well, I'll plug in then. So I'll plug in, substitute in other words. And what do we get? Well, for y double prime, I get r squared e to the rt. That's y double prime, because each time you differentiate it, you put an extra power of r out in front, but otherwise do nothing. The next term will be r times, sorry, I forgot the constant, capital A times r e to the rt. And then there's the last term, b times y itself, which is b e to the rt. And that's supposed to be equal to 0. So I have to choose r so that this becomes equal to 0. Now you see, the e to the rt occurs as a factor in every term, and the e to the rt is never 0, and therefore you can divide it out, because it's always a positive number regardless of the value of t. So I can cancel that from each term, and what I've left with is the equation r squared plus ar plus b equals 0. We're trying to find values of r that satisfy that equation. And that, dear hearts, is why you learn to solve quadratic equations in high school. In order that at this moment you would be now ready to find how spring mass systems behave when they are damped. This is called the characteristic equation. The characteristic equation of the ODE, or of the system, of the spring mass system which it's modeling. The characteristic equation of the system.